Today we will solve a course scheduling problem. Here you are given a list of courses and you are also given their dependencies. That is, which course depends on which course. So the course on which some other course is dependent is called the prerequisite course of that course. So you are given a list of such pairs. So pair AB denotes that A is dependent on B. So we have to find, given this list, is it possible to complete all the courses or not? So it fits into the category of directed graphs. Since there is a notion of direction here, let's look at this small graph. So here course 0 is dependent on course 1 and course 3. And course 0 is also dependent on course 2. And course 2 is dependent on course 3. So here there is no cycle. If you consider a undirected graph, then you would think that 0, 2, 3 is a cycle. But if you see the direction, then from 0 you can come to 2, from 2 you can go to 3, but from 3 you cannot go back to 0. So there is no cycle here. So if there is no cycle, there is no cyclic dependency. That is, one course is A is dependent on B, B is dependent on C. So let's look at this. So we have a course A which depends on B, B depends on C, C depends on D, and D depends back on some other course, maybe B or even A. Then there is a cyclic dependency. It can never be completed, since for A you need to complete B, for B you need to complete C first, for C you need to complete D first, but for D you need to complete B first, but B you can complete only after completing C and D. And D you can itself not complete without completing B. So whenever there is a cycle, there is no possibility of completing the course. So here the task is that to detect whether a cycle exists or not. So this problem is also same as detecting cycle in directed graph. And let's see the input format. Here you will be given a list of pairs. So you will be given 01, 02, 03 and 23. So we have added all the edges. So it's kind of edges are given of a graph. There are different ways of representing a graph: adjacency matrix, adjacency list, and this is what is called edge list. You are given a list of edges. So you have to detect cycle in it. How we can do that? We start DFS from any node, and there is some notion of called back edge in graph theory. So we will not see too much detail of that, but let's briefly give you an idea. So let's say I start DFS from a node. I visit some node. There will be more neighbors of this. So, but I am not yet explored those. I will take one of the neighbors and keep going. And let's say it ends here and we come back here. So we have not yet done with this node. We are just exploring it. There are other neighbors remaining. So this is in process of visit. And this is also in process, this is also in process, this is also in process. Let's say there is no neighbor of this node. 1, 2, 3, 4. So there is no neighbor of 4. And we return from 4. So now this is completely visited. And we come back to 3 and we look at its other neighbors. So 3 is not yet completely visited, but it has been explored, but not completely visited. 4 is completely visited, since there is nothing to do here. But 3 we can come back again. We visit its other branch and then come back to 3 and look for other possibilities. So that we will call in process of visit. Let's represent by V, and all the completed one we will represent C, and all the other nodes with no label we will leave it as it is. So these VVV are still in process of visiting. C has been completed, and here we come to this, so we mark it V. And if there is some node some edge going back to one of the nodes which has been explored but not completely visited. Then we will call this edge as back edge. So if there is a back edge, there is a cycle. If there is no back edge, then there is no cycle. Let's say these all nodes are explored. So what will be the state? And let's say this node edge does not exist, and these all we have visited, we have returned back, and we have not returned from here. This is V, and we come here. So if there is some edge like this, from this to this kind of edge, then we will check that the edge goes to a complete node. So if it's completed, then it's not a back edge. But if it goes back to a node like this, which is not yet completed but just visited, it's in the process of visit, then there is a cycle. Let's look at this example where there is a cycle. So here I have reversed the direction of 3 and 0. So there is a cycle here. So let's start BFS from any node. Let's pick a random node. Let's pick 2. So we come here 2. We see its neighbors. So 2 is currently being visited. So its neighbor is just 1, 3. So we come to 3. 3 is also V. Then neighbor of 3 is 0. So we come to 0. And 0 is also V. Then we look at neighbors of 0. So first neighbor is, let's say, 1. We can encounter in any order. So let's make it as long as possible. So first neighbor of 0 is 1. So we come to 1. We mark it V. Then we look at neighbors of 1. There is no neighbor of 1. Since there is no outgoing edge, incoming edge is not counted. That is, this node was adjacent to 0, but not 0 is not adjacent to 1. So now there is no neighbor of 0 or 1. So we mark it as completed. So we are done with 1. Now we come back to 0 and we look at its other neighbor. It has one more neighbor, 2. So we see that its neighbor is 2. So we will try to visit 2. So we will see that 2 is neither unvisited nor completed, but it's V, that is, it's still being explored. So this edge will become back edge, and this will be the cause of cycle. If we remove this edge, then there will not be any cycle. So this edge from 0 to 2 is a back edge. And let's start from any other node, the DFS. I'm just trying to make the point that no matter from which node we start the DFS, we will ultimately discover that back edge, and we will ultimately discover the cycle. So let's start from 1. So if I start from 1, we look at its neighbor. There are no neighbors, so we mark it complete. Then we look for any other unvisited node. So we see that 0 is unvisited, so we come to 0. It's V now. It's being explored. Its neighbor is 1, but 1 is already complete, so we will not go there. And since 1 is complete, it's not a back edge. So this edge is not a back edge. So this complete, we will not go there. Let's look at other neighbors. 2. So we come to 2. Then its neighbor is 3. Then its neighbor is 0. So we see that 0 is being visited, started visiting but not completed. That is the back edge, and we will mark it as back edge. So in this case, 3, 0 serves as the back edge. So if there is a cycle, let's say there is a cycle, then which of them is back edge? Well, that depends on from where you start the DFS. If you start DFS from here, you will come here in this direction, and when you reach here, you will see that next edge is this one, which is not yet complete. So this will be back edge. If you start DFS from let's say here, then you will move in this direction, and when you reach here, this node, this edge will become back edge. So any of the edges of this cycle can become back edge depending on from where you start the DFS. But no matter from where you start, you will discover the back edge. There is a back edge if there is a cycle. So this we have to find. So at any moment, there are 3 states of a node. A node can be in 3 states. This is a node N. It can be unvisited. It can be visited. Visited means being explored. We have reached here and we are exploring its neighbors, but we have not yet explored all the neighbors. Being visited, let's call it. And this is unvisited, not yet touched. And final is completed, explored node and all its neighbors and the corresponding branches also. So there may be many branches. So we come here, mark it visited from unvisited. So it goes from U to V. So this will be the transition. It comes from U to V. When we come to any node, we mark them as V. And when we return back, so when we have visited all of these all will become C. And we will look at its other branch. When we have explored all the branches, all the nodes, then we look for any other unvisited node. It may be coming like this. Then we will mark this as C. We are done with this part, and this will become V, and we will start exploring the other. So let's look at a case where there is no cycle. So let's look at this case. So let's start from 0. Its neighbor is 1. Come here. There is no more neighbor. It's complete. Its next neighbor is 2. This is V. This is also V. Its next neighbor is 3. It becomes V. There is no neighbor of 3. So we mark it as C. And then we go back to 2. Look at its other neighbor. There is no other neighbor. So we mark it as C. Then we come back to 0 and look at its other neighbor. Its other neighbor is 3. But we see that 3 is completed. It's not V. So this is not a back edge. So there is no more neighbor of 0. So we mark it complete. So we have done the DFS. Now every node is visited. So there is nothing to explore, and we did not encounter any back edge. And this we will call it as forward edge and not back edge. We are concerned mainly with back edge, where edge goes from one node being visited. So both of them are in V state, that is second state, U to V to C. So both of the nodes are in V state. Then this is back edge. So let's write the code for this. This time I will make a change. I will first write it in Java and then C++ and then Python. So just for example, you are given the number of courses and the course number starts from 0 to n-1. So it completely aligns with our indices of vectors and lists. So that's a good thing. And you are given a list of pairs where pair consists of 2 courses. One is the prerequisite of other. You need to follow the consistency, that there is an arrow from 1 to 0. So for all the pairs, just maintain the consistency. That is, arrow goes from first to second. You can take the opposite also, but keep it consistent for all the pairs. So first let's do it in Java. So we will create adjacency list, which will denote the nodes which are adjacent to a given node. So if let's look at one of the examples. So adjacency list for this will be one head for each course or each node. So this is one main vector, and each of them is a vector in themselves, which stores the adjacent nodes. So what are the nodes adjacent to 0? It's 1 and 2. So here we will store 1 and 2. Next, there is no outgoing edge to 1, so it will be empty. For 2, it's 3. For 3, it's 0. So this will be the adjacency list representation of this graph, and it's very useful for representing any graph. If you are not familiar with it, try to study about adjacency list. It's a building block for solving any problem you encounter with graphs. It's very important. So let's build this adjacency list first. So this pre-denotes the pair from this prerequisites array. So P will take the value of this, next it will take the value of this, and so on, all the pairs. And the first one we will assume an arrow from first to second. So in the adjacency list of first, we will push the second one. Now this adjacency list is built. We will keep an array visited. And here initial state will be 0, which will denote U state, unvisited. And then when it's being visited, we will mark it as 1. And when it's completely visited, we will mark it as 2. So there are in total 3 states. So if it's unvisited, so this is basically starting a new DFS. So from a given node, you can only visit all the nodes which are reachable from there. There may be some other nodes which are not reachable. So we will call DFS. So first let's define the DFS here. So this 1 denotes, let me write here, zero means unvisited, 1 means being visited, 2 means completely visited. So this is the condition where there is a back edge. We will only fire a DFS on adjacent nodes of a neighbor, but if we see that its adjacent node is still being visited, that is, we just came back from there only and we are again going back to there, so there is a back edge. Otherwise, visited v equal to 1. So look at its neighbors. So if for its neighbor also it returns false, we return false. That is, if there is a back edge in any of its branches, then return false, else we will return true. And now we are ready to do this. And let's try. Okay, this is a two-dimensional. We are looking at the neighbors of just this node V. Now our answer is wrong, false, true. Okay, so we have not done the main thing here. So when we are done with this node, we store the visited V equal to 2. So it will never get the value of 2 and it will keep returning false even for non-back edges. And here also we need to return true here if it did not encounter any such case. For any of the DFS it did not return false, then finally it will return true. So these are the two mistakes. Hopefully that should fix it. And now we are getting the correct result. Now let's take this negative case. So it gives true false as expected. So let's submit. And the solution is accepted in Java. And let's look at some details. For 46 test cases, it takes around 3 milliseconds. So it's right here in the top, around more than at least 90% for sure. So let's now write down this same thing in C++. Now we have constructed this adjacency list. And initialized visited to 0, that is unvisited states. And then this looks fine. And C++ solution is also accepted. So we will now do it in Python 3. And the solution is accepted in Python as well.